in this particular problem, it's pretty straightforward. It's just what is the escape speed from a 300-kilometer diameter asteroid with a density of 2,500 kilograms per meters cube. So here is a visual just to help you visualize. Here's an asteroid, and then here I've just called this particular length here R. I know the problem gives you diameter, but if you've been exposed to this particular content, you need the radius of the asteroid. And here, the density of the asteroid is given, not the mass. So keep that in mind as you listen in. Okay. All right. So in order to find the escape speed, all you have to do is set up the physics function where you make a statement. The energy that's put into the system, the kinetic energy that's put into the system, must equal to what the gravitational potential energy is that you owe the planet. Okay, so if you can visualize, there's an asteroid here, and then if you put a rocket on top of it, in order for you to leave the asteroid, you have to put in enough kinetic energy to overcome the gravitational potential energy that the asteroid is holding on to you. All right, so in order to do so, all you have to do is set up Ke is equal to U. As long as Ke is at least U, you can escape the asteroid. If Ke is less, then you remain bounded. Ke could be greater than U, so if Ke is much, or if Ke is just greater than U, then you become unbounded. Okay, so in order to find the minimum escape velocity here, all you have to do is apply this particular statement. All right, so on the left side, I'm just gonna go ahead and break it up into 1/2 mv squared. Here V is V escape because we're looking for how much energy is needed to escape. Okay. The mass on the left side here is the mass of whatever object that is trying to escape this particular asteroid. On the right side, the gravitational potential energy function is given as Gm m over r. So you notice here on the right side there are two m's. Here I just put capital M and little m divided by r. Okay. So as I stated earlier, if you've been exposed to this, you do need r, not necessarily the diameter, but the problem gives you diameter, so to find radius is pretty light work. Okay. So I do want to point out on the left side and on the right side in my work here, I have little m and big M. On the left side, the little m is the mass of, let's say, like a rocket that's trying to leave the asteroid, whatever it is that's trying to leave the surface of the asteroid here. Okay, so on the right side, big M would be the mass of the asteroid, little m would be the mass of the object that's trying to leave the asteroid's surface and trying to escape the asteroid's gravitational well. Okay, all right, so here I'm just going to cancel m out. So as you can see, whatever object it is that you are referencing or the problem's referencing, it doesn't really matter. Okay, so in order to escape the asteroid, all you have to do is actually consider the mass of the asteroid and how big it is. All right. So here, in order to solve for V escape, I'm just going to go ahead and do a little algebra. I'm going to move the 1/2 to the right side or multiply both sides by 2. So that'll leave me with V escape squared is equal to 2Gm over R. So once again, M here in the numerator is the mass of the planet or asteroids or whatever it is you are trying to escape. Okay. All right. So in order to find V escape, we're just going to have square root both sides in order to get V escape by itself. So V escape is just radical to gravitational constant times the mass of the asteroid here, and then divided by the radius of the asteroid. But here I know what G is. G is simply 6.67 times 10 to the negative 11. And then R is given, really is just half of the diameter. So once again, the unit here is in kilometers. So half of 300 is 150 kilometers. But keep in mind, this is in kilometers. So 150 kilometers is just 150,000 meters. Okay, so make sure you pay attention to units. You notice here this is in kilometers, but then the density of the asteroid is given in meters cubed. So make sure you always scan out units before you start cranking out calculator work. All right. So the only thing that's holding me back in my function here is what is the mass of the asteroids. I don't know if the problem didn't give me the mass. It did give me the density. So I'm just going to go ahead and just make this general statement. Density is equal to mass over volume. We're dealing with a three-dimensional shape here. Okay. I know my picture for the asteroid here is not perfectly spherical, but because it never said the asteroid isn't, for you to do this particular problem, you have to assume that the asteroid is like a planet, it's like a spherical object. Okay. Therefore, because it is assumed to be a spherical object, you can simply replace volume with the function for a sphere, which is 4/3 pi r cubed, and that's what V is. The volume of a sphere here is just 4/3 pi r cubed. All right. Other than that, we can just go ahead and crank out the math. D here is just the density, and the density here is 2500, which is given in the problem. The 4/3 is a coefficient as part of the function. Pi is in the front, and then here r, once again, is just half of the diameter, and the half of the diameter is 150 kilometers, but you convert that and then you get 150,000 meters, and then don't forget the cubit. And if we punch all that in our calculator, we'll get a value of about 3.534 times 10 to the 19th kilometers. No, excuse me, kilograms, not kilometers, kilograms for the mass of the asteroid here. And once I find that mass, I can just plug it back to my vesc, and that's pretty light work. So here I'm just gonna plug in all the values without, well, I left the units out for capital G because it's kind of long. But here it would just be 2 times g, which is a constant, times the mass of the asteroid, which I just found, and then divided by the radius of the asteroid here, once again, make sure that things are in meters. And then once you do that on your calculator, you get the escape speed for this particular asteroid with this particular diameter and density to be about 177 meters per second. Okay, that's it for this one. Pretty straightforward, nothing tricky. It just has to do with density, so use density to find mass, and then once you find mass, you're kind of done with this particular function. All right, stay nerdy, don't be whack.